So now you can hear me. The question was, how many of you know the purpose and the use of hydroxyapatite? So probably you can, yeah, right. They're not so like, I thought that probably you will need more introduction. So you know that hydroxyapatite is used as implant material, and why is it so? Because it's biocompatible, and it has very good osteoconductivity and very good surface properties. Among all the calcium phosphates, hydroxyapatite is one of the best, and is used in stomatology and orthopedics. So you can use it as an implant for tooth or some kind of part of your bones. But there are some preconditions to use these materials as implant materials. You have to know that one of the main these preconditions is that this material surface has to be with very good architecture in means of pores, pore size, porosity, etc. And now I would really need my presentation so I could show you some great things. There's nothing working. So we can get to the next slide. Oh, okay. Some parts of the slide has been cut off, but this one is the bone chemical composition, and the main part of it is mineral phase. Mineral phase of bone is mainly hydroxyapatite. That's why this material was chosen to all experiments. And there you can see implant materials which are used already in commercial use, like thin implants, etc. Oh, great. I chose two biopolymers for our researchers. And both of them are biodegradable and biocompatible, and it's citizen and sodium alginate. Citizen is very proper for this research because it's aminopolysaccharide, which has a very unique structure, and all the amino groups can be modified, so we can get the desired properties for further researches. As well as alginates have been already used in pharmaceutical industry as they are thickening and gelling agents. Model drug, there is lidocaine. Hydrochloride was chosen because it's a local anesthetic drug. And probably, as you all know, when you are changing something in your body, when you implant something, you have to know that there are many risks like inflammation or pain. And lidocaine, if it's localized in the site where the implant is put in, it can make your life better. It can take off your pain. All the process of developing this kind of material takes a lot of time. It can take more than 10 years until we make this material, synthesize it, characterize it, till it gets to the medical devices. Now we are only on the first two stages when we are synthesizing our hydroxyapatite in briquettes and modifying with different polymers and drugs to make it better. So mechanical properties and in vitro and vivo studies are only in front of us, and only after that we can use it for human bones. Here you can see the graph. As I said, that we are only in the first stages. The preparation of all these hydroxyapatite polymer and drug compositions. There are three main groups. Here is hydroxyapatite which is coated with hydroxapatite, which is impregnated with lidocaine, and hydroxapatite, which is coated with alginate. All these integration cycles were filtered in biothermic scaffolds by using vacuum integration technique in 700 millibar pressure. And more than one integration cycle, like more than one time, you have to integrate polymers because they are low soluble water. And for using two integration cycles, we could get the amount which we need for further integrations of lidocaine or next protein. These integration cycles of lidocaine cause a loss of polymer because polymers are more soluble in weak acids than in water. That's why there were changes in the rates of lidocaine and polymers, and we couldn't detect them by only mass changes. That's what we used to establish whether there are some kind of chemical reaction or what happens there. We used Fourier transform infrared spectrometry to see what happens. The first one is for sodium alginate. This one is for lidocaine. It's for hydroxapatite, and this one is for composite material. As you can see, the main bonds are for water, which is in hydroxapatite as well as in lidocaine and as well as in alginate. And in composite material, you can see the characteristic bonds which are in the three raw material. So this means that there are no chemical reactions occurred during the integration cycle. The same properties, things we can say about composite materials which are made from citizens. Now we will look at the same mixture, and after we have made the first cycle of hydroxapatite, which is coated with hydrogen and integrated with lidocaine, you can see the outer structure, the pore structure of it, and the inner structure when the lidocaine crystals are crystallizing in ancicular morphology. And these coatings, the order of them and the polymer which is used for the coating is very it changes the structure and crystallical structure of lidocaine in what it crystallizes. Here you can see the scaffold, which is first coated with alginate and only then impregnated with lidocaine. Here you can see the difference between which was in previous slides with this one. And now you can see the lidocaine crystals are more rectangular and they are all over the surface. That's why it's called citizen, and they were directly in some parts of pores, like groups. If you take this concrete composite and coat it either with alginate or in next slide will be citizen, then you will see that the structure of them is still changing. So it means that whenever you take another step, you get another structure of this lidocaine, and that impacts further this drug release. As we saw with sodium alginate, this one slide is the first step, this one, and when you coat it with citizen, you get another picture of it, because citizen is the one which makes lidocaine crystals to be more needle-like. All the prepared scaffolds were placed in phosphate buffer solid, and they were integrated in 37 degrees Celsius for more than a week. And at the first time, the 100 microliter outputs were taken for like half an hour, 2 hours, 3 hours, etc. And the content of lidocaine was detected by high-performance chromatography. So this release amount was plotted against time of incubation, and you can see the first initial burst, which happens for the staples which are coated with glycogen. It happens in the first 6 to 12 hours. So if we coat the staples with alginate, then we get better drug release, which is slower, and it can be up to 86 hours. When only then complete drug release has happened. And this means that use of glycogen coatings, you see that there are more than one position. The use of glycogen coatings makes this drug release more faster than if we use an alginate coating. And as a conclusion, it is concluded that there are no chemical reactions between either of these raw materials that could occur during the integration cycle. Each coating of polymer affects lidocaine crystals and their morphology, and the release time shows more promising material for drug delivery from such staples could be alginate, as the completed release occurs only after 86 hours. I would like to say that this work has been partly supported by the European Social Fund within the project Multidisciplinary Research in the Field of Technology of New Sciences Group, and I would like to thank you. And if you have any questions, you can really ask them.